Okay, so now that we have actually looked into how the electron structure has come to be and what we believe the electron structure looks like, the probability of the electron cloud in that area, and we've drawn it in a couple different ways. We did the electron configuration, we did the orbital notation, and we recently did these Lewis dot diagrams. The Lewis diagrams are different because they only show the valence electrons, right? Why are valence electrons important? Anyone know why valence electrons are so important in chemistry? That's your bonding stuff. She's exactly right. That's what you use to bond, okay? So if we're using it to bond, where are we going then? We're moving from atoms and elements into compounds and molecules, right? Okay, so atoms are like a single little thing. Molecules are more than one atom stuck together, right? So we're going to look at how can we're going to look at how do we bond, basically. I've always just showed you what ionic and what covalent does and learned how to name them and learned the difference between them, but we've never necessarily looked at how do they actually bond, okay? So I think the first ones we're going to start with are ionic substances and drawing Lewis diagrams or electron dot diagrams for ionic substances, okay? So we're going to title it Lewis diagrams of molecules. I don't want to say of molecules, I want to say of compounds. Because molecules have those direct bonds, and some compounds don't have those direct bonds, they just give and take the electrons, right? So Lewis diagrams of compounds. We're going to look at ionic first. Before we really look at the Lewis diagrams, let's just go quickly. What's over ionic? What can we call ionic? Metal, non-metal bonding. We always write the metal first because it appears first on the periodic table. It's on the left side. So metal, non-metal bonding. Okay. Does anyone remember the definition of ionic bonding? Good. They take electrons or they give electrons. One person is always the giver and one person is always the taker. Right? Which one gives and which one takes? Sorry? So this is the give and take of electrons. Let's look at a simple one that has just one atom of each. So I'm going to look at lithium and chlorine. So lithium chloride. Just by looking at the charges, you guys know lithium's a +1, chlorine's a -1. Swip swap, we need 1 and 1, right? But let's look at a more detailed approach of it. Okay, so if we're looking at lithium and chlorine, I'm going to have this side of the room. Can you draw the Lewis diagram of lithium? This other side of the room, can you draw the Lewis diagram of chlorine? If I am not back in time, maybe you guys draw them both. What's your Lewis dot diagram of lithium? What does it look like? What's your Lewis dot diagram of chlorine? What does it look like?
No, it's like chlorine.
Okay, over on this side, what does lithium Lewis dot diagram look like? An Li with a single electron dot. Why is it a single electron dot? Because it's in column 1, it only has one valence electron. Good. Okay, over here, what about your chlorine? What does it look like? I'm going to draw it with a different color. It's a Cl with 7 electrons around. 1, 2, 3, 4, 5, 6, 7. You guys okay? Now, this is a give and take relationship, right? That's what we said. I hope I wrote it fast enough. This electron partners up. Now I'm going to do something here. Lithium gives its electron over to chlorine. This is great. Chlorine thinks it has a full valence shell, right? Lithium gave away its last electron in its valence shell, so it actually pops down to the next valence, or the next shell, which is full already, right? So lithium now acts like helium because it's up, down, or it passed back down into the next shell, right? So it's now in the 1s2 shell, and it's feeling happy because it has a full valence shell. And chlorine over here took that electron from lithium, and it now has a full valence shell, right? So this is the electron, the Lewis dot diagram of it, but when we draw ions, we have to include them. So basically, we draw square brackets around each one. Lithium lost an electron, so what's its charge? +1. Chlorine gained an electron, so its charge is -1. And this will be the Lewis diagram of an ionic bonded substance. Okay? Shall we try another one? Shall we try manganese? No, magnesium. Let's do magnesium. And do you want magnesium and bromine? Okay? So let's look at magnesium and bromine. Okay, what did you guys do? Some people might look and go, okay, it's magnesium and bromine. How many of each do I need before I start drawing stuff? Okay, that's one way to do this. Magnesium, it has a charge of +2. Bromine has a charge of -1. So how many bromines do you need? And how many magnesiums do you need? Okay, so you kind of know how many of each you need to borrow or to draw now, right? Can I tell you something? The one that has 1, you put in the center. The one that has 2, you put around the outside. If you needed 3 and 2, you'd start with the bigger number. You'd go through the one that had 3, then the one that had 2, then the one that had 3, then the one that had 2, then the one that had 3. Makes kind of like a salty line, okay, of ions. So the other thing you could do is you could draw magnesium. How many valence electrons? Okay, so we go across the outside. I usually go horizontally with my things, but you can draw them vertically as well. Okay, magnesium bromine is 7, so we draw around 1, 2, 3, 4, 5, 6, 7. Now, we need another bromine. And so we could put this bromine on the other side. I need Br. 1, 2, 3, 4, 5, 6, 7, 8, right? So, oh, I didn't draw 8, I only draw 7. I'm really bad at counting. Yes. How do we get 7 for bromine? It's in column 17. So it's in the column right before, and we only count the S's and the P's, right? So we count 1, 2, and then we go over to gallium. We count 3, 4, 5, 6, 7 valence electrons, okay, to get to bromine. So basically, if it's in column 17, it has 7 valence electrons. Column 16, 6 valence electrons. It's kind of something we've been memorizing, right? The charges for your periodic table goes on how many electrons you need or how many electrons you lose. So if you lose electrons, you're getting more positive, okay? So, for example, this magnesium is going to give away this electron over here and give away this electron over here. How many electrons did it lose? 2. So it's going to now have a +2 charge. Okay? So if I come in here, I would most likely erase this one and erase this one because I moved them, and come here and write a +2. That bromine over here, how many electrons did it gain? It gained that 1 electron here, right? So it has a -1 charge because it gained an electron, and electrons are negative. And I put square brackets around these, -1. Some people get used to it, they see the pattern, and they can draw this without moving the electrons out. That's fine. If you get to the point where you don't need to move the electrons out for the give and take, you can draw it in the first place without moving them, go right ahead, okay? Now, big thing, people go, do I have to draw those 8 dots? Yes. When you draw the 8 dots, and the ones that have taken the electrons, the ones that give away the electrons, their outer valence shell that they once had now has nothing in it. It's dropping down to the next valence shell. So to represent that, we don't have any dots in theirs. Okay? Do you want to try one on your own? Okay. Do you want me to give you a tougher one or one of these smaller ones still? Okay, so I'm going to look at calcium. Let's go calcium fluoride. Calcium and fluorine. Can I change fluorine? Can I make it sulfur? I'm going to change it and make it sulfur. Calcium and sulfur. So try calcium and sulfur. Okay, so just double checking. Some of you I heard go, okay, calcium's a +2, sulfur's a -2, that balances, I need one of each. That's great. Other people will just draw them and try and play with the electrons and see if they work or if they need to add more or less, right? So if I draw calcium, how many valence electrons? 2. So I got like here and here. Then sulfur, how many valence electrons? So 1, 2, 3, 4, 5, 6. Okay. Lots of people can see that this calcium can send over its electron here and give its electron up over here. And it ends up with calcium giving away all its valence electrons. Yay, it's happy. And sulfur ending up with a full valence shell of 8. Everyone is happy when they feel like they're noble gases, right? So how would we actually draw this Lewis diagram? It would be calcium with square brackets. Do I put any dots? What's the charge? Because it has lost 2 electrons. Then sulfur with a -2. Do I have to put any dots? Yes, I put all 8 dots around because It was given the 2 electrons to get a full valence shell in what it already had. Is this okay? You don't have to draw the dots in little colors or different colors. I like them because then you can definitely see that those weren't their original. But when you're actually drawing your Lewis diagrams, they don't have to be in 2 different colors or 3 different colors. They can all be just in a pencil. Okay? I'm going to throw a whopper out to you guys. Let's do aluminum and oxygen. Okay? So I'm going to leave you to think about aluminum and oxygen. I'll give you a few minutes. This will be our last of ionic, then we'll jump into covalent. So aluminum and oxygen. Okay, so try and figure this one out. Okay, so I see a lot of you are on the right track. Some of you figured out how many of each you needed. Some of you just started drawing. So when we look, aluminum has 3 electrons. Oxygen has 6. Right? So right now, if I'm going to give away my electrons, this aluminum can give 1 here and 1 here, but does oxygen want any more?
So can you make another oxygen?
So then we have to draw another oxygen. Okay? So if I draw another oxygen, it has 6 electrons. I give aluminum away. That aluminum's happy because now it's down to a full valence shell, but is this oxygen guy happy? No. So I need another aluminum. Aluminum has 3 valence electrons. It can give away 1 valence electron here. That oxygen's happy.
So you need one more oxygen to get out.
But we need another oxygen because aluminum has to give a couple more away. So, in the end, here, aluminum's happy, it gave away all its 3 electrons. Oxygen over here is happy because it has 8. If you went out and figured out aluminum plus 3, oxygen minus 2, I need 2 aluminum, 3 oxygen, take a look, here's how and here's why, right? Through the bonding of your valence electrons. Now we just have to draw this as a nice diagram, right? Because this is just all wibbly wobbly squishy stuff. Okay, so how do we make a nice diagram? Well, realistically, you got to find an end point and a start point on this. So if I look here, this oxygen, then the aluminum, then this oxygen, then this aluminum, then that oxygen, kind of if I wiggled around that line, right? So I would start with oxygen. Do I draw 8 electrons around the oxygen? Yeah, because it took away those electrons or took those electrons. What charge on this oxygen? Minus 2. It took 2 of aluminum's electrons here. Then aluminum, do I draw any electrons around them? No, they gave away their electrons. How many electrons did they give away? 3, so this is a plus 3. Then we have oxygen. We draw all 8 because it took 2 more to make a full valence. And we draw aluminum again, plus 3, and then we draw our final oxygen, minus 2. So that's the Lewis diagram of Al2O3. Do you have to alternate oxygen and aluminum? Yes. And I'm going to tell you this. Positives and negatives, do they like each other? Opposites attract, right? Is what we always say. So even with magnets and stuff, opposites attract. Positive and negatives attract to each other. If it's a positive and positive, they're not going to want to sit next to each other. So we don't even draw them sitting next to each other because that's not how it happens. Opposites attract. It goes positive, negative, because then they'll just sit nicer there. Okay? Is this okay for ionic? That should be pretty much a full page for you. Right? Flip the page if you've got a full page. If you have half a page, maybe you want to continue on. We're going to talk covalent. We have time to talk covalent. My band students leaving today? Sorry, I get confused sometimes. There's no band. Okay. Covalent. What do we know about covalent molecules? Non-metal, non-metal. And how do they deal with their electrons to make full valence shells? Do you remember that term? They share their electrons. Remember we talked about ionic and covalent as relationships way back in grade 10 science? And this is the nice sharing relationship where they hold hands and all that other stuff. Okay, so they share. They're sharing electrons. Now, before we really jump into the Lewis dot diagrams, I want to explain things, because remember, we can't look at charges, so there's no such thing as charges, because we're not giving electrons away or taking electrons, so we don't have any more electrons or we don't have any less electrons. So you can't look at it as charges, okay, ever. We're sharing the electrons to make everyone happy to get a full valence shell. The electrons don't disappear out of anyone's shell. Do you remember the fact that we can have two non-metal elements form different things? So like there's such thing as carbon monoxide and carbon dioxide. This doesn't happen in ionic because of the fact that it's like negatives and positives and they have to balance out. There's only one way of doing that. Sometimes with covalent, they get around this sharing thing and they bond even though they're not perfect. Okay? However, there are certain ones that they really like to be. Carbon monoxide doesn't stay around if it doesn't have to. Do you guys know why carbon monoxide is so deadly? Because if you breathe in carbon monoxide, what does it react with? Does anyone know? Oxygen. So if you're swallowing carbon monoxide into your lungs and oxygen, before the oxygen transfers into your lungs, it'll probably react with the carbon monoxide, right? Therefore, it makes carbon dioxide, and you don't really want that because you want oxygen for your cells to live, right? And carry on cellular respiration. So, I'm going to tell you, well, CO plus O2 goes to give me CO2, but you're going to need two COs and two in front of your carbon dioxide, right? So you'll balance it out. But we can draw them both as covalent molecules. But most often, you guys, we will just draw the one that's most common or the one that works out the nicest. But I'm going to show you other ways of drawing things because sometimes we share bonds and different things like that. So let's deal with carbon dioxide as one of the first ones because it's one that works out nicely. Okay? So same thing when you're doing Lewis dot diagrams of these compounds, you draw the Lewis dot diagram of the atom first. Okay? But here, carbon dioxide, because that's the one we're drawing, it tells us how many molecules of each. It says one carbon, two oxygens, carbon dioxide. Okay? So if we do this, one carbon, how many valence electrons on carbon? Well, that's the charge, plus or minus 4, but there's 4 valence electrons. So we go 1, 2, 3, 4. Now oxygen, we've drawn already, it has 6 valence electrons. We're doing carbon dioxide, right? And oxygen also has 6 valence electrons. We know we have to draw 2. I'm going to draw my oxygen over here just because I know it's going to make carbon dioxide. And I just know what it's going to look like. You could have drawn the oxygen on the other side. Okay? When we share, we kind of group things together. So I'm going to share these pairs of electrons. Oh, that's already paired up. I can't do that. I'm going to share which other electron? This electron with that electron. Does that make sense? So now this oxygen thinks it has 1, 2, 3, 4, 5, 6, 7, 8. Good. This carbon over here, though, thinks it has 1, 2, 3, 4, 5, 6. That's not quite happy yet. But this would be like a carbon monoxide kind of thing that's going on. But usually it likes to bond more because that carbon's not the happiest fellow, right? He wants to share electrons here and here. This is why carbon dioxide is such a stable one, because carbon is sharing all 4 with 4 more, which will make 8 valence electrons for carbon, and that oxygen over there that shared its electrons get the use of carbon's 2 electrons to make it seem like it has. But this looks monstrous and ugly. So anytime they share electrons, we draw lines. Okay? And if you look up carbon dioxide, you would see something like this. Because this one shared 2 electrons, so we draw 2 lines. This one shared 2 electrons, and then lots of times you'll see the non-bonding electrons on the outside. Sorry, I'll extend the page so we can see it up in the back. So wherever we do those big god-awful circles, I shouldn't call them like that, those big ugly circles around the 2 pairs, right? We draw a line for each one. And because of the fact that we had 2 big ugly circles that connected the C and the O on one side, we draw 2 lines. This is called a double bond. Same thing on the other side. Okay. Good. Do we have to draw the dots? For a Lewis diagram, you must draw any non-bonding electrons. Okay. So yes, we do need to draw those extra dots. Now where do I get how many dots I need to draw? I look at my picture here. I had 4 on this oxygen that didn't connect or pair up. All my carbons were paired up, so I should have no extra ones on carbon. But then my oxygen one, there's 4 more there. So let's try. Do you guys want to look at oxygen? That's a molecule you know of. Or what other molecules that you know of that you want to look at? Nitrogen dioxide. That would be well, nitrogen dioxide, nitrogen trioxide. Do you want to look at one of those? Sure. So let's talk about let's just do N2, just nitrogen gas. So we're going to look at nitrogen gas here. Nitrogen gas is just N2. Can I leave you to try this? I think I can. I'm going to leave you some time to try it. Then I will show. So when you guys drew it first, the first thing you did was draw nitrogen's single atom ones, right? Nitrogen has 5 valence electrons, And this nitrogen over here, it has 5 valence electrons because it's an N2. What did you end up doing? Sharing these ones, sharing these ones, sharing these ones. It might have not been in that order, but you shared 3 sets of electrons, right? So if we shared 3 sets of electrons, we can write it as N triple bar N, which is N triple bonded, and then for each nitrogen, okay, that's a good question. It doesn't matter where you put the dots. Eventually we're going to talk more about what Jesse was talking about, the fact that positive and negative and different things, and how the bonding and the electrons actually work. We try to put them farthest away from any of the electrons or bonds, but in sets of pairs. So we go directly across from where they were already bonded, is what I would do. Okay? So we're going to leave you be. Tomorrow is science fair, right? And we'll come back after the break and do more of these.